Hello, welcome back to A Boring Revolution, your number one news source for everything in regards to the Boring Company. Welcome back. We've got a new episode for you today. It is part 2 of our secondary tunnels or our feeder tunnels. We're going to talk about today how we're actually going to build them, how we can construct them cost effectively, quickly, and something that's fit for purpose. So let's get going with that. Excuse me, guys. So, secondary tunnels and feeder tunnels part 2. So as we discussed in part 1, feeder tunnels are critical to this system and its usability. There will be a lot of feeder tunnels along the system. Every sort of 3/4 of a mile you'll have the start of a feeder tunnel. Therefore, they're going to be quite a big part of the construction process. So we need to think about how we're going to build them, where we're going to build them, and what techniques we are going to use to build them. Let's discuss how we can build these tunnels. Prefabrication. As much as possible, we want to build elements off-site in a factory or some kind of warehouse somewhere, and then bring it to site ready prepared to be installed. And the bigger those elements are, the less work we need to do on site. So in terms of our steel prefabricated wall units, we need those to be built off-site, ready to put into the shaft as we are excavating it. And the same goes for the other techniques which I'm going to discuss in a minute. Pipe jacking. Pipe jacking, the actual pipes or steel sections, they're going to be prefabricated off-site, but that whole system is a very mechanized way to dig short sections of tunnel and is perfect for these secondary or feeder tunnels, and that's the system we're going to use and discuss today. Modern methods of construction, where possible, we're going to use modern methods of construction, or we're going to attempt to mechanize the process as much as possible in order to speed up and do particular construction jobs simultaneously, and that's what we're going to use that for. So, if you remember this particular sketch from our previous episode, we have our pods in our feeder tunnel. Today, we're going to talk about our elevator shafts and also the shafts or our launch pits where we start doing our pipe jacking. So we have our 3 elevator shafts. Obviously, it doesn't have to be 3 elevator shafts. I've just chosen that as a nice reasonable number to use for today's example. However, you could have 5 shafts, you could have 7 shafts, maybe even 8 shafts if you need to. That will lower the overall cost if you have more shafts on a particular row of feeder tunnel. What we're going to be building today is this part here. These ramps here, and the one that's hidden behind my head, these ramps here, they will be constructed using more traditional methods, simply because they are relatively short, so it doesn't really matter, and obviously they're a ramp. It's going to be a lot easier to use that system rather than go to pipe jacking, just because of the complexity of trying to curve the actual tunnel in the direction we need it to go, and do it in a way that's basically controllable and we know where we're going to go. And we want a more accurate, more traditional system, which is going to be relatively easy and reasonably quick to construct if we use the right number of man hours on that job. So here is pipe jacking. It's very, very similar to how a TBM operates. However, there's 2 critical differences. The first one being, is this jacking rig, it is in the shaft itself, it is not inside the tunnel. Usually have these very, very large jacks. Often there's more, there's only 4 on this particular example. However, you could have potentially 10, maybe even 14 jacks. We have our thrust ring here. The thrust ring is connected to the jacks and it pushes forward each segment or casing, and they are jointed together every sort of 10 to 14 foot, and then they are pushed into the the actual tunnel area, and then obviously this jacking rig is withdrawn, and then a new set of casings or segments are added. It is pushed as one single entity, and that's the main thing. So you obviously need to lubricate this area on the external of the actual tunnel lining to ensure that it is pushed through without having to use huge rams or thrust cylinders. You want it to be able to push it through relatively easily. Here is a system of pipe jacking that I found. The actual company involved seems to be one of the only ones that uses this kind of rectangular pipe jacking segments. I've never seen it done like this. I've always seen it done with actual circular cylinders. However, it would make perfect sense for the boring company to use this kind of rectangular cylinder because you wouldn't actually need it to be as wide. There'd be less wasted space. You could have it so it's only, say, 11 foot 4 inches wide, and then say 10 foot 8 inches tall, and that would be perfect for vehicles, and there'd be a lot less wasted room. However, with a circular cylinder, you need that to be at least 11 foot 10 inches in diameter, at least. So it would make sense if we could find a company that does it like this, or subcontractor, or maybe buy that subcontractor and then utilize their technology on our projects, because obviously we want to bring this kind of pipe jacking in-house into the boring company. Here's a good cross section. As you can see, this one has some very large thrust cylinders. There's our thrust ring, and then I think they're using concrete segments on this one. You can use steel, you can use concrete. It's better to use steel because the actual profile of the steel is a lot thinner. It can be up to 70% thinner than the actual concrete segments. Therefore, I'd recommend that the boring company uses that particular system. The actual front bit of the pipe jacking machine is very different from a TBM. It's a lot more complicated to do than a traditional TBM, because not only, if you go back to this one, not only do you have it's not manned, but you're injecting slurry into the face of this machine. You're also injecting it up here and around down the sides of the actual steel segments or casings, and then it comes, I'll show you on this one here, it actually, the pools here, the actual spoil and the slurry pool down here at the bottom, and it's collected and then it's pumped to the surface, and the actual slurry and the spoil is separated, and then that slurry is pumped back to the face of the machine to essentially lubricate it and also assist with the withdrawal of the actual spoil from the face of the machine, and it's done relatively quickly. You have this thing called a crusher cone that sits behind the cutter head or cutter disc, and what that does is it spins with the actual cutter head, and all the segments or small pieces of rock and stone that are grinded up are then pushed into where this crusher cone is, and the drive unit spins that, and it crushes it into very small pieces between about 4 millimeters and about 9 to 10 millimeters, and then that's mixed with the slurry, and then it's pumped to the surface, and there you go. Rather than having big sort of conveyor belts and trains removing the actual spoil, you do it via this slurry, which actually works out quite well and is a bit quicker. So it is certainly good in terms of the cost. So before I explain the actual system and how it's constructed and put together, I just wanted to explain what influenced my choices of construction methods. And the main thing that influenced me is obviously LA or California is an earthquake zone, so we have to take into consideration the possibility that LA may be struck by a large earthquake. Maybe it's 7.9 or 7.8 on the Richter scale. So we have to have this system withstand or sort of take up quite a large earthquake and resist that. And sort of 3 of our elements are based on that. So Obviously, it needs to be fit for purpose. It needs to be the right diameter for the vehicles. It needs to be able to stand the test of time. It needs to be corrosion resistant. So again, it must be fit for purpose. It must be built specifically for this system and work in harmony with this system in terms of its specifications. Stiffness. If you've ever designed a building or talked about a building that has to live in an earthquake zone and be subject to those lateral and horizontal forces, you need the joints and all the structural elements to be stiff, specifically in the joints. So the intersection between the columns and the floor plates and the roof or any other, or the lift shaft or whatever is in that particular building, everything needs to be stiff at the joint area where the horizontal and vertical structures intersect. And that is a very important part of why I designed the system the way I did, with a lot of steel, because I wanted to ensure there's a great deal of stiffness. Regularity basically, in a nutshell, without explaining this for 10-15 minutes, regularity is how each of the structural elements react in an earthquake situation where you've got large lateral loads coming into that structure. You need the wall sections, the foundation sections, the actual concrete sections to all act in a similar sort of in unity almost. If one particular element is moving a lot more or moving in a different direction than other structural elements, then there's a high probability that that particular structure will fail in an earthquake. So what you want is regularity. You want all the structural elements to be moving in unity laterally in conjunction with all the different construction like systems that you've got in that particular structure. Redundancy basically is you over engineer a structure and you build in some kind of redundancy that in the event that one particular structural element fails or is compromised, then the second method, or your redundancy, falls in and takes up the slack of that particular structure, speed and efficiency. So obviously we want to build our shafts, we want to build our tunnels in a speedy way, but we also want to do that efficiency. A good example of that is the Empire State Building. That was built incredibly fast in less than 15 months. However, they just threw men at the job. So in terms of like man hours, it wasn't that efficient. So what we want is low man hours and a very quick and easy structure to assemble. And that's basically one of the core sort of principles of this system that I have chosen. So in terms of earthquake, we've got stiffness, regularity, and redundancy. Let's have a look. So this is our drone view. We are above our site. If you've not already noticed, I have added some more shafts. I've added this drive shaft and I've added this reception shaft. They have a dual use. They're not going to be wasted at the end of the job. I'm going to find a use for them and I'll explain that in a minute. But the drive shaft is where we start off with our pipe jacking, with our thrust cylinders. They're going to be based here and it will be pushed through perfectly level, perfectly straight line all the way through. All our elevator shafts are pre-constructed, so you'll actually see the machinery being pushed through, then pushed through here, pushed through here, pushed through here, and then finally here, where it will be craned out and then it will be shipped to another site. This particular tunnel here, linking the main arterial tunnel, that will be constructed in part 3 of this series, and I'll be explaining how we do that with traditional methods. So yes, we have our 3 elevator shafts. It doesn't need to be 3, it could be 5, it could be 8 elevator shafts, but you'll definitely have 1 drive shaft and 1 reception shaft, and they're about 6.5 meters deep. So we have our cross section. So as you can see, we have our drive shaft and our reception shaft. We have our elevator shafts A, B and C. Reception shaft and drive shaft are slightly deeper than the elevator shafts. One of the core elements of my structure I've designed here is these concrete ring beams. As you can see, we have these kind of, it looks a bit like a top hat. And what that is doing is it is tying that entire shaft or that excavation into the bedrock. I'll explain how we're going to do that in a minute. But the drive shaft and the reception shaft form part of the ramp that goes down into the main arterial tunnel, but also they will be converted into emergency exit stairwells once the pipe jacking has been completed. So you'll have some you might have an elevator in there, but it's more like a staircase. You'll have a staircase that runs up the wall, up to the surface. In the event of a fire or even an earthquake or something like that, people can get out of the pods and they can go up the shafts via the stairwells here. So here's another cross section. If you remember that top hat I was speaking about a minute earlier, that's the concrete ring beam. This sits here at the top of our excavation. This is our excavation. Just to note, this is our excavation for our drive shaft or reception shaft. It's constructed with welded steel plates or lagging panels, 155 millimeters thick, box section steel. That's all prefabricated off-site, guys, in a factory. It comes in big units ranging from 5 foot tall, maybe up to 7 foot tall, and very long, almost could be potentially 16 foot long, maybe slightly shorter than that, maybe 15 foot long, and then they're all welded together on site to provide one very stiff structure. The floor as well is made of these welded plate steel panels, which again are prefabricated off site, brought in, craned into the excavation or the shaft, and then at the joints here they are welded to the wall lagging panels. The actual steel welded plate floor panels are sat on these concrete pad foundations. You can see this wavy line here. What this is our micro bore piles, which are tying in our top hat concrete ring beam into the bedrock, some 35 to 40 foot below. That'll be determined by geological survey to determine how deep those micro piles need to go, but they'll be at least 35 to 40 foot deep, I would imagine. This is just a further progress of this particular excavation. So we've added this this concrete floor slab, which is 240 mil. It's heavily reinforced, again, to ensure that we've got that regularity in the structure and increase the stiffness. In between our concrete pad foundations, there is a void underneath this steel floor panels. So what we've done is we've filled that with injected concrete screed filler. It's a very liquid concrete that is just injected in there at high pressure just to fill any gaps, so that the actual these steel floor panels are sat actually on the bedrock rather than just on these foundation pads. We have this steel cutter shoe. On hindsight, having drawn this, I think that once completed and the excavation has reached its finished level, the bottom 3 inches of that cutter shoe should be cut off and then welded flat, because potentially that could have an impact if there is an earthquake. It may affect this wall or these walls, so we'd cut the sort of last 3.5-4 inches of that steel cutter shoe off once it has been used. We have our thrust wall plate, which is for our pipe jacking. That is installed here. Basically, it is various I-beams stacked together with 14 mil plate steel. Again, same on the other side, and then box section steel here. We use quite a lot of box section steel on this particular structure. I like using box section steel. It's very easy to use. I mean, certainly in the UK, there's a lot of contractors that have got good experience using box section steel, using steel plate and welding that steel plate. And And there's all box section steel in our floor panels, our prefabricated floor panels, and in our prefabricated wall panels. So just having a look from the top of our excavation. This is our elevator shaft. It is very, very slightly different from our reception shaft in that we can use thinner prefabricated wall panels, because obviously the excavation is not only slightly less wide, but is a lot less in terms of length as well. So we're using our micro bore piles. As you can see, they run around the top here. Obviously our tunnel is running here, so we can't use micro bore piles on this section here. They are 40mm micro bore piles with a 16mm bore. That means it's basically the hollow inside. You inject grout into the middle of the micro bore piles at very high pressure, around 14 to 16 bar pressure, and that further solidifies into the bedrock, ensuring there is a nice firm connection between the bedrock, the actual micro bore pile, and our concrete ring beam, which is this bit here. As you can see, it stretches around the entire excavation, and the perimeter of that, we've got box section steel, 80mm by 80mm, and our steel plate lagging panels are here. That's all prefabricated offsite. It's incredibly robust. It's going to be very difficult to bend. Once this has been installed, it will be filled with some more rebar, and that, in conjunction with the box section steel, is then filled with a very liquid concrete mix. It'll use a lot of sand, a lot more sand than a traditional concrete mix. It'll also use a fine aggregate or smaller stones to ensure that it's a more liquid, and it can be poured in there to again further add redundancy to this particular structural element. Okay, it's been quite a long presentation this, but to make this work, it requires a lot of thinking and a lot of structural elements to interact with each other. So let's go to the key questions. Why so much steel? I like using steel. Steel can be welded together. Once it is welded, that actual weld is stronger than the steel itself if done correctly. If you have that kind of bucket style design with our top hat and our ring beams, that is incredibly robust. It allows us to ensure that regularity in the structure, and you can do that with concrete, but concrete it takes a long time to set and cure, requires a lot of man hours to pour it. With steel, it can all be prefabricated off site. Is this earthquake resistant? Absolutely. This will be a very, very earthquake resistant structure. As I've just spoken, it covers all those three elements, and thus it will stand the test of time, even in a 7.8 Richter earthquake. How long does pipe jacking take to build? You can comfortably do 25 to 40 meters on a good day with perfect conditions. Obviously, it will depend on the geology of this site, but I'd imagine we'd be able to get close to 30 meters per day, maybe slightly above that. Will this cause a lot of disruption? Unfortunately, it possibly will do for a short period of time. In our particular example, we are sinking 5 shafts. Potentially, they could be sinking maybe 8, 9, or even 10 shafts. So that's going to cause some disruption at the surface. However, all those shafts can begin construction at the same time, so we're minimizing the amount of disruption. Once the excavation has been completed, we can cover it up with some steel plate, and then normal sort of road conditions can resume. So you probably have maybe 2 weeks of disruption while you're doing all your work, and then after that it should hopefully return back to normal almost. But yeah, it will cause some disruption. Can these shafts be built quickly? Very quickly. All the shafts can begin construction at the same time. We're using prefabricated means. We're going to use a couple of small excavators on this job in all the shafts that we use. Therefore, it's quite mechanised, and we could quite easily do these shafts very, very quickly. It shouldn't take more than a few days, really. Why not 100% pipe jacking? Well, I'm going to cover that in episode 3, but basically it's just too complex to do the whole thing in pipe jacking. It's better to do the long and straight section in the pipe jacking, get that done very cost effectively, and then for your ramps, throw in lots of man hours on there for the last sort of 40 to 50 meters, and that can be done relatively quickly because it's only 40 to 50 meters and we've got large numbers of men on site. Right guys, thank you for watching. Appreciate this has been a long episode. Please like and subscribe to the show. Thank you for watching, and hopefully I'll see you guys around on episode 3. Thank you very much, and I'll see you next time. Don't be boring. Goodbye.